Okay, good evening, everyone. Welcome to this live stream classroom. So everyone can, hear my voice clearly. Okay, so you can always leave a message in this classroom, in this chatting panel, and let me know if you have any questions or encounter any problems. Okay. Okay, so if everything works fine, I will start today's lecture. Okay, let me see. Okay, thanks for this responses. Okay, and again, welcome to this live stream classroom. And my name is Hao Han from Tsinghua University, and I'm now an associate professor at the School of Vehicle and Mobility. Today it is a very big pleasure and honor for me to give you this lecture. Okay, so today we're going to be talking about automotive industry and carbon neutrality, which is a very hot topic in recent years. And hopefully I can finish my talk within like 40 minutes to 1 hour. And after that, we can have some discussion around today's topic. Okay. Okay, so now that we are talking about carbon neutrality, so the first thing we need to know is what is carbon neutrality and why carbon neutrality is so important. And actually, if we put the carbon neutrality in the context of China, it goes back to President Xi Jinping's address at the UN General Assembly. He stated that China will strive to peak carbon dioxide emissions before 2030 and achieve carbon neutrality before 2060. And this requires tremendous hard work, and China will be making every effort to make these goals. And after President Xi Jinping's address, China has initiated the so-called 1+N policy framework to facilitate the realization of the 30-60 greenhouse gas mitigation targets. And the so-called 1+N, the one represents the one central document that is released by the central government, which outlines the core actions needed to cope with to realize the carbon neutrality target. And the N represents the numerous accompanying documents that specifies the detailed actions needed for different economic sectors, for different sectors, for example, the transport sectors, the residential sectors, and for example, the power sectors. Okay. So after implementing the 1+N policy framework, and actually we must realize that China will be making a lot of efforts in the coming decades to make carbon neutrality happen. So that will affect every person, every company, every government in China. And so everyone is talking about carbon neutrality, and it becomes really very important for us. Okay, so some students said my presentation is not full screen. So I'm not sure if this presentation is not full screen for everyone. Maybe you can, okay, let me. Oh, I'm sorry. Is it full screen now? So this presentation is full screen. Oh, I'm sorry. Let me see. Yes, it's the second slide, but it's full screen on my side. But I'm not sure. I don't know why it's not full screen on your side. So can you see these details very clearly? If it doesn't affect our presentation, then I think I will go on maybe because I really don't know what is happening. Okay, the picture is clear. Okay, so I hope everyone can see the details. Okay. So I'm sorry for this. I'm sorry for this problem, but our time is limited, so I don't think we have some time to check what is happening. Okay, so I might maybe if you can really see this picture clearly, so I will go on maybe. Okay. Okay, and actually, it's okay. Thank you for your response. And actually, it's not only for China. Even globally, carbon neutrality has been a very big trend for many regions of the world. Actually, by the end of 2020, more than 100 countries has made commitments in carbon neutrality, just as UN Secretary General Guterres, he addressed at the Columbia University, which is a very famous address, the state of the planet. He said that this means that by early next year, countries representing more than 65% of global carbon dioxide emissions and more than 70% of the world economy will have made ambitious commitments to carbon neutrality. So we must realize that carbon neutrality has really become a global trend, and it will be very important on the global level. Okay, so after knowing that carbon neutrality is really very important for us, and the next thing I would like to talk about is carbon neutrality is not only important, but it is also very difficult when we put carbon neutrality in the context of the transport sector. So this figure shows, this figure is what we call a so-called Sankey diagram. It shows the energy flows of the world. And each, there are a lot of flows in this figure, and each flow with a different color, it represents a flow of a certain energy. And if you look at the purple flow, which represents the so-called oil products, including like gasoline, diesel, kerosene, all these oil products. And these oil products is a very important, part of the global energy flow. And we can find that over half of the oil products flow to an end sector is transport. That means like transport sector is responsible for half of global oil consumption. Oh, still the same slide? Oh, I'm sorry, I will try to share my slide again. I'm really sorry for this. Okay, so can you see the new slides? Yes, okay. That's the first one. Thank you very much. I'm sorry for this. I don't know what happened, but okay. Okay, so this is the Sankey diagram. As I mentioned, the energy flow, each flow represents a certain flow of the energy. So if we look at the purple flow, that represents the oil products, which means as gasoline, diesel, kerosene, and half of the purple flow flows to an end sector on the right hand of the figure, that is transport. So transport is really very important, and it consumes half of global oil products. And if we translate this energy consumption into CO2 emissions, and we can find that CO2 emissions from the transport sector, it represents 1/4 of overall anthropogenic energy-related CO2 emissions. So as this left-hand figure shows. And if we look into this 1/4 emissions, and we break down these emissions into different subsectors, we can find that road transport, it accounts for 3/4 of the total transport emissions. So road transport, which is car, trucks, and all this kind of stuff, they are really a very big generator of CO2 emissions. So that's the very big impact from the transport sector in terms of the CO2 emissions. And another challenge we are facing is that actually the transport demand is still increasing very fast. So we have to reduce CO2 emissions in the context of increasing demand. As the left-hand figure shows, this figure shows the vehicle ownership level in different regions of the world. And different colors represent different regions. And if we look at the developed countries like the United States and Europe and Japan, all these regions, they typically have a very high level of vehicle ownership. For example, in the United States, the vehicle ownership level is already higher than 800 vehicles per 1,000 people. And even in EU and Japan, their level is over 500 vehicles per 1,000 people. But if we look at other regions of the world, especially when we consider some very big developing countries like the so-called BRICS countries, Brazil, Russia, India, China, or South Africa, all these countries, they have a very big population basis, but their vehicle ownership level is still on very low level. So they will still have a long way to go in terms of vehicle ownership increase. So that means we will still have a very big potential for the vehicle ownership increase. So in that context, we have to cut CO2 emissions while maintaining increasing transport demand. So that will really be a very big challenge for us. And another big challenge we are facing in the transport sector is actually in some, the segments of the transport sector, they are among the most difficult to decarbonize sector. For example, if we look at the heavy road transport or shipping or aviation, and all these sectors, they are very difficult to decarbonize. And the International Energy Transition Commission, which is a very famous international organization, they define these subsectors as so-called the harder to abate sectors, which means they are very difficult to abate in terms of CO2 emissions. And currently, we are not fully clear how these sectors can be decarbonized. So that will be a big challenge in terms of the carbon neutrality for the sectors. Okay, and after talking about the CO2 emissions, the very big impact for transport sector, and it's a big difficulty in decarbonizing these sectors. And next thing I would like to talk about is how we can conceptualize CO2 emissions from the automotive industry. That means if when we are look, I'm sorry. I'm so sorry. Oh. So I have switched the page to page 8. So can anyone see this page, or is still stay on page 4? Yes, page 8. So it's page 8 now. Okay, so if I now I'm turning to page 9. Can anyone tell me if it's 9 or still page 8? Still page 8. Oh, page 9. Oh. So someone tells me it's page 8, and someone tells it's page 9. I'm not sure. This currently on my side, this is page 9. Whoa. Oh. I'm sorry. So now it's page 9. Okay, so maybe if I turn this not to screen mode, maybe we can. So is it page 10 now? Yeah. I guess it's page 10 now. Okay, so okay. I'm sorry. Actually, before this presentation, I checked my presentation with the staff, but it's working a while ago. But working okay a while ago. But I'm not sure what happened. So I will use my slide without the full screen mode. I hope everyone can see this slide normally now. Okay. So this is page 8, and this page actually conceptualizes how the CO2 emissions is generated from the automotive industry. Actually, from this figure, we can see actually 2 dimensions from from this figure: the vertical dimension and the horizontal dimension. First, let's look at the vertical dimension, which is represent the CO2 emissions from vehicle manufacturing. That is from the top to the bottom. That is the mining of the ores, the refining of the ores, and the vehicle manufacturing, vehicle use, and finally the vehicle recycling. So for each of the stage, we need a lot of energy input to do this, right? So there will be a lot of CO2 emissions from all these processes. So typically, we call these CO2 emissions from vehicle manufacturing the vehicle cycle emissions. Okay, so again, if you look at the horizontal dimension of the automotive industry, you can find that we typically call D represent CO2 emissions from fuel production and use, from the recovery of oil to oil refining, to oil transport, to refilling, and finally to vehicle use. And typically, we call these CO2 emissions the fuel cycle emissions, or in some circumstances, we call them the so-called well-to-wheel emissions. Okay. So when we talk about automotive industry CO2 emissions, we are actually, in most circumstances, we are referring to these 2 dimensions of CO2 emissions. Okay, so some of you may ask that what is the relationship between these 2 parts of emissions? And this figure gives the answer. And there are 4 bars in this figure, and for each bar, there are 2 parts of the emissions. The green part of the bars represent the vehicle cycle emissions, and the blue part of the bars represent the fuel cycle emissions. And if you look at the left-hand bars, which represent CO2 emissions from the conventional vehicles, and we can find that for conventional vehicles, the vehicle cycle emissions, which is the CO2 emission from vehicle manufacturing, these emissions represent only a very limited part. It's normally 15% to 20% of the total emissions. And the majority of the emissions come from the fuel cycle emissions, which is the emissions from fuel production and finally fuel use, okay? So that's for the conventional vehicles. And if you look at the battery electric vehicles on the right-hand side of the figure, we can find that for battery electric vehicles, the structure changed very significantly. And for the vehicle cycle emissions, it increased a bit, mostly because of the manufacturing of the batteries, because battery manufacturing is a very energy intensive and emission intensive processes. So when we manufacturing batteries, it brings the CO2 emissions from electric vehicle manufacturing higher than conventional vehicles. But if we look at the fuel cycle emissions, we can find that the fuel cycle emissions from battery electric vehicles is significantly lower than conventional vehicles. That's mostly because of the switch from the conventional oil use to electricity use. Okay, so even in China, even China's energy mix, in China, the fuel cycle emissions of electric vehicles is already lower than conventional vehicles. So by using this figure, I want to show you that if we want to decarbonize the automotive industry, then we have to both reduce the CO2 emissions from the green part and from the blue part. So we have to make vehicle manufacturing and vehicle use both carbon neutral, so that we can reach the carbon neutrality of the automotive industry. So next, I will separately talk about how we can decarbonize the fuel cycle emissions and how we can decarbonize the vehicle cycle emissions. Okay, first, let's talk about how we can decarbonize the fuel cycle emissions. And I guess many of you might have think of the electric vehicles. Okay, so actually, electric vehicles has been very essential to the decarbonization of the transport sector. And actually, in the past several years, global electric vehicle market has been increasing very fast. And as remarked by a very famous expert, it is now entering the steep growth phase. So what is steep growth phase? Actually, when we consider a new product entering the market, it typically follows a so-called S-shaped curve. So we can imagine the S-shaped curve. In the beginning of the curve, it grows very slowly, and in the middle part of the curve, it grows very strongly, and at last, it will grow very smoothly again. So when we talk about a steep growth, we mean that we are growing in the middle of the S-curve. So it really will be growing very fast. And this figure shows the global electric vehicle market penetration in representative markets. For example, if we look at China, in 2020, the market share for electric vehicles has reached like 5% of the total vehicle sales. And in Europe, this market share is as high as 10%. And in some parts of Europe, for example, in the leading market in Norway, Norway is the country that has the highest market penetration for electric vehicles. It has reached as high as like over 70%. So we can see that for Norway, this country generally has finished the process of electrification. So it's really growing very strong. And actually, when we look at it this year in 2021, especially in the recent months, both in China and Europe, the monthly sales of EVs has accounted for like 20% of the total sales of total vehicles. Okay, so we are expecting that by the next year, 2022, the share of electric vehicles in the market will be like 20% for major markets of the world. And by 2025, the share will be 30%. And by 2030, it will be like 50%, okay? So 2030, only less than 10 years from now, there will be 50%. That means 1 out of 2 vehicles will be electric vehicles. So really a very strong growth ahead. And if we look at the CO2 emissions from electric vehicles, we are pretty confident that even if we look at CO2 emissions currently, the life cycle CO2 emissions from electric vehicles, it has already been lower than conventional vehicles. And this figure shows the comparison of the life cycle CO2 emissions from conventional vehicles and battery electric vehicles in 4 representative regions of the world. From left hand to right hand, that is Europe, United States, China, and India. And for example, if we look at Europe and the United States, it is already very clear the CO2 emissions from electric vehicles is lower because, for these countries, the electricity is relatively clean, especially in Europe, the electricity is, there is a lot of green electricity mix. So it's very natural that the CO2 emissions from electric vehicles is very low. But even if we look at China and India, someone may argue that, in China and India, both these countries are burning a lot of coals to produce electricity. And maybe when you use electric vehicles in these two countries, it might, it might be very dirty for electric vehicles. But actually, when we have a careful calculation about the life cycle CO2 emissions from electric vehicles, even currently, the CO2 emissions from battery electric vehicles is already lower than conventional vehicles. And this is a calculation from the ICCT, which is a very famous international organization. And the calculation is very confident and very careful. So we are pretty confident that the CO2 emissions, they can reduce CO2 emissions. Electric vehicles can reduce CO2 emissions currently. Okay, so if we look into the future, the CO2 emissions of electric vehicles is basically determined by where the electricity comes from, right? So although the current electricity mix in different regions of the world is a bit different, but if we look into the future, like this figure shows the electricity mix in different regions of the world, from the left hand to right hand, United States, European Union, China, India, and world. And if we look at the current status in 2019, we can find that, yes, the mix is very different in different regions of the world, right? In United States, European Union, the clean energy share is a bit higher than the other regions. But in China and in India, the grid is pretty dirty because, the brown part of the electricity, this is from coal power, so it is pretty dirty. But if we look into the future in 2070, we can find that almost for all regions of the world, there will be a full transition from the conventional grid to a 100% clean grid. So that means if we use electric vehicles at that time, the electric vehicle will be very green and will be very low carbon, near zero carbon emissions. So that will be the future for electric vehicles. So we must be very confident for the future of electric vehicles because the grid is turning green. Okay. And another very important question is, yes, we realize that in the future, we will use green electricity, so the electric vehicles will be green. But someone might argue that, yes, we want to use green electricity, but electric vehicle the only way to utilize green electricity? Yeah, this is a very important question, actually. Actually, the answer is no. The answer is no. Actually, besides electric vehicles, we have numerous other options that can utilize green electricity. For example, if we have green electricity, we can use the green electricity to electrolyze water to get hydrogen, and we can use that hydrogen on fuel cell vehicles, and that will also be a solution to use the green electricity. And a step forward, we can also use the green electricity to produce the so-called power to liquid, to use electricity to produce gasoline or diesel. And we can even use this green gasoline and green diesel in conventional internal combustion engine vehicles. Okay, so actually we have a lot of ways to utilize green electricity. So we have to make one thing clear. What is the most efficient way of using future green electricity? So that's very important. And this figure perfectly shows what's the energy efficiency for different utilization pathways. If you look at the efficiency, from the left hand, that is the direct electrification. That means we use green electricity directly as electricity and on the electric vehicles. So if we use electricity from this pathway, we can get 77% of the energy. 77% of the energy can be utilized to power the vehicle. Okay, so but if we use the green electricity to generate hydrogen and then we use hydrogen on fuel cell vehicles, then the overall efficiency is only 33%. So only half of the electrification pathway. So because there is a lot of energy losses along the whole chain, especially on the electrolysis, that's only 76% efficiency, and especially on the fuel cell use, because fuel cell use is only like 50 or 70% energy efficiency. So there will be a lot of energy losses. And one step forward, if we look at the power to liquid pathway, that will be even very poor efficiency. It's only 20% or 16%, only 1/4 or 1/5 of the electrification pathway. So that will be a very substantial losses of energy along the energy chain. So when we look at this figure, we must realize that if we have green electricity, then we better use it as electricity itself, and it will provide us with the highest efficiency. And if we look at the transport sector, actually we are pretty confident that most of the sectors currently can be powered by direct electrification. Especially under some very extreme, very special circumstances, the battery cannot do the job, but we have to rely on hydrogen. But for most of the transport segments, we can use battery electrification. So if we can use battery electrification, we do not have to turn to other options. Okay, so that's the major point from this figure. And another question is, yes, we know that CO2 emissions from electric vehicles can be lower, but what is the cost for doing this? Can we, if electric vehicles, if the cost of electric vehicles is pretty higher than conventional vehicles, then is it cost effective? So that's one question that we need to answer. Actually, back in like 5 years ago or 10 years ago, electric vehicles is really very expensive. Maybe 5 years ago, I still remember that at that time, a lot of electric vehicles are derived from its counterpart conventional vehicles. So if we compare these counterpart vehicles, we can find that the cost for electric vehicles is about 2 or 3 times higher than conventional vehicles. Okay, so that's 5 years ago. But currently, if we look at the cost of electric vehicles, as the upper right-hand figure shows, this figure shows the so-called TCO. TCO is total cost of ownership. That is the cost including vehicle purchase and fuel cost and the maintenance cost and insurance cost, all the costs from the consumer perspective. Okay, so this figure shows the TCO of conventional diesel vehicles, hybrid electric vehicles, and battery electric vehicles. And if we look at the red dots of the 3 bars, that means that the final TCO of the 3 pathways, we can find that currently the TCO of battery electric vehicles is already at the same level with conventional vehicles. So that means we do not have to spend more money to switch from conventional vehicles to battery electric vehicles. Why? Because even if the cost of electric vehicles is higher than conventional vehicles, but when you use the electric vehicles, the electricity is cheaper than the oil, than the gasoline or diesel. So overall, the total cost of ownership of electric vehicles is on the same level of conventional vehicles. So that's the current status. And if we look into the future, why electric vehicles is so expensive? Mostly because of the battery. Battery is very expensive. But this figure, the mid figure shows, battery cost has been decreasing very fast over the past decade, and it is still decreasing. And we are expecting like another half cut by in the next decade, by 2030. So at that time, we believe that at that time, the cost of electric vehicles will be even lower than conventional vehicles. So, very perfect for electric vehicles. On one hand, you can reduce CO2 emissions, and on the other hand, you can even at the same time save a lot of money for you. So that will be a very cost-effective solution for decarbonizing the transport sector. Okay, and another very important point we need to know is plug-in electric vehicles is not only important for the transport sector, it is also pretty important for the whole economy and especially for the power sector. Because currently the power sector is dependent on the thermal power mostly. And but in the future, we need to integrate a lot of what we call the VRE, the variable renewable energy. That is wind energy or solar energy. Because for these energies, they are variable. Why do we call them variable? Because they do not, whether it's available, do not, are not determined by whether we needed them. Because, for example, if someday I need some power, but on that day it is raining, there is no sunshine, so I just cannot use use the solar power to meet my demand. So how can we utilize this so-called variable renewable energy? We have to prepare a lot of energy storage devices. And if we do not have the storage devices, then we just cannot fully utilize this VRE energies. So, but if we need to produce a lot of dedicated energy storage devices, then it will be very expensive and it will be very resource consuming. So, but if we look at electric vehicles, actually each electric vehicle, they have a very big battery on the vehicle on board. So we can consider this battery as distributed energy storage devices. So we can use these electric vehicles to serve the grid, to help them to integrate these reliable renewable energies so that we can save a lot of money. So that will help the grid to make the transition more easily. Okay, so electric vehicles will be very valuable not only to the transport sector, but also for the whole power sector and the whole economy. Okay, so we have talked a lot about electric vehicles, and actually people are also talking a lot about fuel cell vehicles. And fuel cell vehicles, actually, they do have a role to play in future decarbonization of the transport sector. Actually, from the in the many subsectors of the automotive industry, the fuel cell vehicles are taking on plug-in electric vehicles and have a full-line competition between these two options. And from as this figure shows, from the pickup trucks to the heavy-duty trucks and all the way to the flying cars, fuel cell vehicles, we can see both the fuel cell vehicle models and the plug-in electric vehicle models, and they are having very hot competition against each other. But if we look at the market performance, especially when we look at the light-duty segment performance, we can find that actually the fuel cell vehicles are not having good performance in terms of its commercialization. For example, if you look at the left-hand figure, this figure shows the sales of Toyota Mirai in the United States and the EU. Toyota Mirai is a very representative fuel cell vehicle model, which is represent maybe the highest sales of all the fuel cell vehicle models. But even for this, we can find that, for example, in the United States, its highest sales is only lower than 2,000 units. And for in Europe, it's only several hundred. So that's really a very small number, compared with the millions of sales in these two regions every year. Okay, so and again, if you look at the trend, it's even worse because especially in the United States after 2019, there's a very significant drop of the sales of this vehicle model, especially in the pandemic. But actually, even in the pandemic, at the same time, the sales of electric vehicles, plug-in electric vehicles, they have seen a very strong growth even in the pandemic. So there's a very significant comparison between these two pathways, and it's very likely that from the market performance, we can conclude that maybe fuel cell vehicles might never have a chance in the light-duty segment, and many of us are believing this. Yeah, and the right-hand figure shows the light-duty fuel cell vehicle models under commercialization from major OEMs around the world. Yes, the OEMs actually are making great efforts in commercializing the fuel cell vehicle models, but it's really not competitive at all. Especially when you compare them with the electric vehicles. Okay. And if we look at the CO2 emissions from fuel cell vehicles, very similar to the electric vehicles. The life cycle CO2 emissions from fuel cell vehicles is basically determined by where the hydrogen comes from. Okay, so distinguished by where the hydrogen comes from, we typically categorize hydrogen into three major categories. That is gray hydrogen, blue hydrogen, and green hydrogen. And the gray hydrogen, it represents if the hydrogen comes from fossil fuels, mostly the coal-based hydrogen or natural gas-based hydrogen, then we call the hydrogen a gray hydrogen. And even based on the fossil fuels, if we remove the CO2 emissions by using the so-called CCUS technology, carbon capture and utilization storage technology, then the hydrogen becomes the blue hydrogen. And blue hydrogen is zero emission, but it has emissions, but we just remove the emissions by using the CCUS technology. And one step forward is the green hydrogen, which is basically based on the renewable energy. Basically, it's a wind or solar energy to generate electricity, and then we use electricity to electrolyze water to get hydrogen. So that hydrogen is green hydrogen. So if we use different sources of hydrogen, we can have very different CO2 emissions from the fuel cell electric vehicles. Okay, so this figure shows the life cycle CO2 emissions from numerous representative of vehicle pathways. So, and 6 of them are related to fuel cell vehicles, from the first pathway to the next pathway. And if we look at these 6 pathways, we can find the highest emissions comes from the 8th pathway. That is, the fuel cell vehicles are using hydrogen from grid power and electrolysis. So that means, well, we, because in China, the grid power is mostly coal power, right? So actually, firstly, we use coal to generate electricity, and then we use electricity to electrolyze water to get hydrogen. So both the region of the energy is very dirty, and again, the whole process is very low efficiency. So you get the highest CO2 emissions from this pathway, right? But if you look at the 7th, for example, the 6th, 7th, or 9th pathway, the CO2 emissions is pretty low because most of these pathways are originated from the renewable sources like the surplus water and hydropower and also thermochemical hydrogen. And so we get very low CO2 emissions. So the life cycle emissions of fuel cell vehicles really determined by where the hydrogen come from. Okay, and one very important behind this is yes, we love green hydrogen and we hate green hydrogen. But how fast can we switch from gray hydrogen to green hydrogen? This is a very important question. Actually, currently, we must realize that most of the hydrogen we are using currently is gray hydrogen. Not because we love gray hydrogen. We do not love gray hydrogen, but we have to use gray hydrogen because it is the cheapest. It is much cheaper than green hydrogen. So people are rational. They just choose the cheapest solution. Okay. So if you look at this figure, from the left-hand side is the SMR without CCS, which is basically is the so-called gray hydrogen. It's coal hydrogen or natural gas hydrogen. And currently in 2019, the cost of the gray hydrogen is really offering the lowest cost. So people will choose this cheapest hydrogen. And even if we look into the future, into 2050, 30 years from now, even at that time, if we look at the right-hand bars, the blue bars represent the hydrogen from electrolysis, mostly from the green electricity. Then we get the green hydrogen. So even in 2050. If you look at the range of the blue bars, we are not 100% confident that the cost of the so-called green hydrogen will be lower than conventional gray hydrogen. Even in 2050, we are not 100% confident it will be realized. So that means even in 2050, there might be still a significant share of conventional hydrogen, and only because of the cost of the green hydrogen is very difficult to be lowered down. This is very different from electricity because, for electricity, the switch from the conventional electricity to green electricity is already happening because, the green electricity the cost is lowering down very quickly. In many parts of the world, the wind or solar electricity is already, the cost of them is already lower than conventional electricity in many parts of the world. So the switch is already happening. But for hydrogen, the switch is very difficult to happen. There is a basic economy behind that, but I will not say that. But you have to know that the conversion from conventional hydrogen to green hydrogen is very difficult, very difficult. And so, what exactly will be the role for the fuel cell vehicles? We have to, it's actually a very complicated question, and I would like to explain this by using the so-called the hydrogen ladder. And we can see there's a lot of boxes on the right-hand side of the figure. And for each box, it represents a certain utilization for hydrogen. And, there are upper utilizations on the upper side of the figure and the lower side of the figure. So if one utilization is on the upside of the figure, that means this utilization is unavoidable. So if, for example, if you look at the red boxes, the long-haul aviation or shipping, for these utilizations, yes, of course you can use, for example, battery electric. But if you use battery electric, then that means you will have to equip an unimaginable amount of batteries on these vehicles. So that means it's theoretically it's okay, but technological is unfeasible. So you have to rely on fuel cell vehicles. You just cannot turn to other options. You have to use fuel cell vehicles. So fuel cell vehicles is the only option for this utilization. Okay, but if you look at the lower side of the figure, for example, the H2FC cars, fuel cell cars, as we have mentioned, yes, of course you can use the fuel cell cars, but unfortunately it is very low efficiency and the car is too expensive. So most of people will not use fuel cell cars. Instead, they will turn to the electric vehicles. So if there are options other than fuel cell vehicles, then the fuel cell will be very uncompetitive. So if we look at this figure, it is very clear. So what the future will be for the fuel cell vehicles? It must be where hydrogen is unavoidable, then where there's a role for fuel cell vehicles. So that might be the future for fuel cell vehicles. Okay, and again, one step forward. Well, although we are promoting a lot of electric vehicles and fuel cell vehicles globally, but we must realize that most of the current fleet on the planet and most of the structures on the planet are prepared for the conventional internal combustion engine vehicles. Okay, so we may someone has asked if whether we can use renewable energy on these vehicles. We want to switch from conventional fossil fuels to renewable energies, but do we necessarily turn to electric vehicles or fuel cell vehicles to make the transition? Can we still stick to the conventional internal combustion engine vehicles? So that's thought from a lot of experts. So actually, the answer is yes. Just as we have mentioned, what we have mentioned from the previous slide, there's a technology called the power to liquid, or normally what we call the e-fuel, or a more popular word, the liquid sunshine. That means we use the renewable energy to generate electricity. Then we use electricity to produce green gasoline and green diesel. And we use this green gasoline and green diesel on conventional vehicles. So that will be a very clean pathway, right? It is really near zero emissions. And still, we do not have to change our fleet. We do not have to change our refueling structures. That sounds very good, right? And there are really a lot of very attractive features from these pathways. For example, if you look at energy density, and if we, in terms of both the volume energy density and weight energy density, if we look at the batteries, fuel cell, and the liquid sunshine, these three pathways, we can find that the so-called liquid sunshine solution, it can provide the lowest volume and lowest weight when we if we want to store the same amount of energy. And it will be far lower than the other battery and hydrogen solutions. Sorry, I see one question. So we will have discussion later, okay? So I will continue my lecture. After that, we can have the discussion, okay? Okay, so so this is very attractive for many utilizations, especially when we talk about like aviation, because aviation for the planes, they are always very sensitive to the volume and to the weight. So if one technology can store the same amount of energy with the lowest volume and with lowest weight, then it is very attractive to be used on planes. Okay, so this is one advantage from this pathway. And another very big advantage is, we just do not have to change our fleet. We do not have to change the refueling structure. We have been building this fleet, building this refueling infrastructure for 100 years. So we do not have abandoned them. We can just change from the conventional fossil-based liquid fuels to the renewable-based liquid fuels. We do not have to change other things. So that will save us a lot of money. So that's one very attractive feature from this pathway. Okay, so that sounds very good, right? For this liquid fuel pathways, and it's really attracting a lot of research and industrial interest over recent years. But we must remember one thing. That is the most substantial weakness for this pathway. Actually, we have mentioned this before. It is the most substantial weakness for this pathway is the energy efficiency is pretty low, just as what we have mentioned in this previous slide. Okay, as we can see here, actually the right-hand two bars is the power to liquid, both diesel and petrol for these two pathways. Yes, they are perfect in many terms, but the energy efficiency is awkward. It's 20%, 16%. So there's a lot of waste of energy along the conversion of these fuels. So that's the substantial weakness for this pathways. So that means the fuel cost will be high, and the whole economy will be less competitive compared with other pathway. So for this pathway, the most likely used for this pathway might be on some very special circumstances like the aviation, like the long haul aviation, maybe in this very special utilizations. Okay. Okay, so we have talked a lot about the CO2 emissions from the fuel cycle. So for the next few slides, I will talk a bit about the emissions from the vehicle cycle. So because the vehicle cycle emissions is relatively a bit complicated, because when we manufacture a vehicle, we need a lot of resource inputs, we need a lot of energy inputs and labor inputs. So all this stuff will be generate certain CO2 emissions. So today I will give you a relatively simple example. That is the CO2 emissions from battery manufacturing, because battery will be the core component for the future vehicles, right? So if look at this figure shows the processes need to produce a battery from the left hand to the right hand. It starts from the left hand, right, from the minerals, and all the way to the right hand side from the to the final product, a battery pack. Okay, so from the left hand side we can see all the things start from the minerals, because you have to dig something out of the planet and use them to produce the product you need, right? So by using the minerals, first we need to dig them out of the mountains or out of the seas, we got, by using minerals, we got cobalt minerals, nickel minerals, manganese, lithium, or lithium brines. Okay, so all these processes, they generally happen in some mining loss or mining mountains, and for example, you need to use some machines to dig the minerals out of the mountains, and you need electricity to power the machines. Okay, so you need to transport these minerals into other places. Okay, so you need some diesel trucks to do this. So all this kind of stuff, you need some kind of precise energy to achieve this, right? So as this figure shows, for this process, what the processes energies we need is diesel, coal, natural gas, electricity, and after that we need to produce some basic chemicals out of the minerals. For example, the cobalt sulfate, nickel sulfate, manganese sulfate, lithium hydroxide, and lithium carbonate. All these basic chemicals. And these processes happen in some like chemical factories, and the process fuels we need like the residual oil, coal, natural gas, electricity. Okay, and after getting the basic chemicals, we can further produce the downstream products like the active materials, cathode, anode, the cell, BMS, and finally to the battery pack. And all these mentioned processes, they generally happen in some so-called battery manufacturing factories, like the big factories from the CATL or BYD or Panasonic or LG. All these battery manufacturers, they provide these processes. And for these processes, there are two major process fields we are using. That is natural gas and electricity. So by looking at this figure, we can make this clear that why we need process energies, and how these CO2 emissions are generated during these processes. So, and we can also, see how these CO2 emissions can be mitigated. Firstly, if we can do some technology improvement, to improve the energy efficiency of different processes, so that we can use less process energy, so that less CO2 emissions can be emitted. Okay, and for example, we can use green electricity, because green electricity is for a lot of processes we are using electricity. So if the electricity can be green, then the whole processes can become green. And furthermore, we can actually reduce CO2 emissions by using recycling. Actually, when you dig the minerals out of the mountains, it is very energy consuming. But if you recycle the minerals from the end of life products, it will normally consume less energy, and it will also save us a lot of resources, right? Okay, and if we look into the essential precise as shown in the last slide, that is battery manufacturing stage, because it is the most important and most energy intensive precise along the whole supply chain of the batteries. If we look into this very special precise, actually it's very complicated inside. This figure shows the major precises, what is happening in these battery manufacturing factories, from homogenate to homogenate coating, drying, rolling, cutting, vacuum drying, lamination, encapsulation, vacuum drying, liquid injection, formation, aging, capacity grading. All these processes happen in these battery factories. And actually, for different processes, we have different colors on these processes. And if one color is darker, that means this process is more energy intensive. So we can easily find that there are three processes, which are drying, vacuum drying, and vacuum drying. All these processes, these represent the most energy consuming processes. And so actually, when you manufacturing a battery, you have to make all these processes happen in a very dry environment. So make this environment dry, you have to do something, right? You have to dry the environment by using some kind of drying machine. So that machine needs, normally it needs natural gas or needs electricity to power the machine. So that's very energy consuming. Okay, so how can we reduce the CO2 emissions from the factory? That's something we need to know. Actually, the most important thing we need to know is reduce the drying demand. Okay, so we can use the segmented drying, infrared drying, or laser drying to do this. And also we can do some overall jobs like improving the efficiency, improving the yield, or using green electricity. And by using all these measures, actually we can do a lot of things to reduce the CO2 emissions from battery matching and reduce them. Okay. And here's a calculation of the CO2 emissions from battery manufacturing. So we have to know the number, right? And there are 4 bars in this figure and representing different CO2 emissions from different battery chemistries. They are all batteries, but different battery chemistries. And if we look at the NCM 811, that is the mainstream battery chemistry that we are using. And if we look at this, the CO2 emissions from this pathway is a bit over like 80 kilogram of CO2 emissions per kilowatt hour of battery. Okay, so if we assume a vehicle with 50 kilowatt hours of battery capacity, that's very typical in China's vehicle market. So that means if we produce this 50 kilowatt hour battery, we need to emit like 4 tons of CO2 emission, right? So that's really not a small number, right? Because even when we consider the manufacturing of conventional vehicles, the life cycle emissions of vehicle manufacturing is only like 6 to 9 tons of CO2 emissions. So only this battery will add another like 4 tons of CO2 emissions to the life cycle emission. So that will be very CO2 intensive. But if we look at other chemistries, for example, LFP, lithium iron phosphate, or sodium-ion batteries, these 2 kinds of chemistries, they just emit lower emissions. Actually, when we look at the Chinese market, the LFP battery is really doing very well in recent months, and they are actually, people are using them more than conventional NCM batteries in recent months. And yes, we are using them because they are cheap and they are safe and they are reliable. But actually, besides that, they also provide a very big benefit. They can reduce the CO2 emissions when we manufacture them. So that's a very big advantage for LFP batteries. Okay, and so we need to answer one question: how we can decarbonize the vehicle cycle emissions. So if we want to realize carbon neutral for the automotive industry, we have to make these emissions very low, right? So this figure shows the many measures and many technologies that can be taken to reduce the CO2 emissions. And many of these measures and technologies are transitional. For example, if we use the recycling, both pyro recycling, hydro recycling, and direct recycling, we can realize like 30% or 50% degrees of CO2 emission reduction. And by cleaning the grid, we can also, gradually reduce the CO2 emissions from battery manufacturing. And at the same time, we have one final solution for this. That is using 100% green electricity plus using electricity as precise energy. And that will provide us with near zero life cycle emissions. Yes. And actually, because, as we have shown in this previous slide, many of the processes are dependent on electricity. So if the electricity is 100% green, then you can imagine all the processes will be very clean. Actually, this is right not only for batteries, but also for a lot of industry products. As long as the electricity is green, then the production of the battery of the product is green. So actually, the future of the industrial decarbonization really depend a lot on the grid, Okay. Okay, so I will conclude today's lecture with this slide. This slide is a slide from the International Energy Agency, and it presents the future scenarios of CO2 emissions from different sectors of the economy. From the left hand is power, energy transformation, industrial transport, buildings, and the direct air capture. If we look at the transport sector in the red box, we can find that from 2040 to 2070, which is 20 years from now and 50 years from now, there will be a substantial decrease of the CO2 emissions from like 4 gigatons of CO2 emissions per year to like lower than 1 per gigaton per CO2 per year. So that will be a substantial reduction of the CO2 emissions. And to achieve this, we have to it depends on very substantial technology innovation and also very substantial industrial transformation. That is, I think, what is part of the so-called future automotive, and that's one part of its its meaning. And that really means a lot of challenges ahead, and I also believe that it will also means a lot of opportunities ahead. Okay, so that's all for my today's lecture. Okay, thanks for your attention, and thank you. And after this, I think we can have like some discussion around today's topic. Okay, so if you have any question, please you can open your mic or to ask me, or you can leave your message on the chatting panel. Maybe yes, I can see one question on the question and answer panel. That's from Dr. Wang Yunfei.